network covalent atomic solids. So here we have atoms that are chemically bonded with covalent bonds to each other. So carbon has several different allotropes, forms of its solid. This is graphite, where we have carbon atoms covalently bonded to each other in thin layers. So there's a sheet of carbon atoms, really a piece of graphene right here, and then there's another piece of graphene up here. And those two layers are held together by dispersion forces. So the layers are not held together very tightly, but the atoms in each layer are held together very tightly. So what happens is this top layer can slide next to this middle layer, which can slide next to the bottom layer. So graphite has a slippery quality, which makes it useful as a pencil lead, because when you pull it along a piece of paper, you're leaving behind part of the graphite, right? It's also good as a lubricant. So you can put graphite in a door lock, and it'll help to lubricate the pieces. It's also a good electrical conductor. So graphite's density is 2.2 grams per cubic centimeter. A diamond has a density of 3.5 grams per cubic centimeter. So that tells us, just from the density, the carbon atoms are closer together here. And what's going on is that the carbon atoms are now bonded to each other in 3 dimensions. So diamonds are formed from graphite, essentially like coal, under extremely high pressure and temperature. So here's a diamond made out of, it's the same substance as graphite, but very different in its properties. So the diamond has a unit cell that is similar to the zinc blende cell, in that we have carbons at the corners, right, and a carbon on the face, but then we also have carbons in the tetrahedral holes. So diamonds, very high melting point, very hard, they used as an abrasive, doesn't conduct electricity or heat. High pressure favors the formation of diamond from graphite. What can you conclude about the relative densities of the two substances? Diamond is denser than graphite, or graphite is denser than diamond? Or can't tell? The diamond is denser. So I'm taking the graphite and I'm compressing it and putting pressure on it, squeezing it, right, to make it more dense. And what I get is the diamond. So the diamond is more dense than the graphite. Another form of carbon, these are called fullerenes, buckyballs. Buckminster fullerene, discovered in the 1980s. So this is like a giant soccer ball. Well, not giant, it looks giant, I'm sorry. It's an incredibly small soccer ball made out of carbon atoms. So this is C60, 60 carbon atoms joined in hexagons. And these have really some cool properties, and you can make them in different sizes. And related to this and to the discovery of graphene, nanotubes. So this is a sheet of graphene. It's 1 atom thick, just carbon atoms bonded to each other. Here's looking at the top of it. It reminds me of chicken wire. Do you guys know what chicken wire is? Yeah. So if you took this ribbon of chicken wire and bent it around, you can imagine making a tube out of it, right? So those are called nanotubes because they're really, really small. And you can also have nested nanotubes, multi-walled nanotubes. So these forms of carbon are cool because they do conduct electricity, and they're also really strong. And so you're going to see these in lightweight applications such as golf clubs and bicycles. And you can also use bundles of nanotubes to make teeny, 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 tiny wires. So some pretty cool stuff with carbon. Another type of network covalent atomic solid is silicates. So silicates are arrays of silicon and oxygen. And so silica has the formula unit SiO2. So someone yesterday asked, well, how is SiO2 a covalent atomic solid when H2O is molecular? Isn't that just a molecule? It's an excellent question. Well, if we look at the Lewis structure here, with silicon bonding to 4 oxygens, we see that each of these oxygens would have an unpaired electron that it could share with another silicon atom. And so this could share with another silicon atom, and another silicon atom, and another silicon atom. And so that's what they're doing. So, this guy sharing an oxygen with another silicon atom, and this oxygen is being shared. So even though it looks like it's SiO4, the ratio is only SiO2 because each of these is also being shared with another silicon atom. So this is the structure of quartz. It's one form of silica. There are other types. You'll see these in ceramics and cement and in glass. Sand is a form of silicate.